Physics is fun and joy. All you need is a good teacher. Come, join me. Why are we defining something called as vectors? These are quantities. Vectors, numbers, scalars. These are all different quantities. Numbers are the most easiest things we have been dealing with, right? To ascertain about the quantities, the number of apples, the number of mangoes, the amount of distance between your home and the office or the schools, right? The number of dresses you have, etc. Similarly, vectors are again a different quantities. And why are we using vectors for? Why shouldn't we just um, suffice with numbers? Aren't they sufficient? Why do we need to go to describe something called as vectors? Why do we need this terminology called vectors? Right? That's the question. That's the question we have whenever we see this term called vectors. So let's address that as the first, right? That is the first question we need to ask in physics, which is why? Why is it? Why is there such a quantity? It's not a wrong question. It's a very perfect and a very pertinent question that physics is looking for such students who ask this question, who who want to know why certain things are there, right? Now, if you see the vectors, they are different from numbers right away. How they are different? For it, let's try to understand what we have been doing with numbers. So there are certain quantities in our day-to-day life for which the representation is just plainly through numbers. Is it not? Right? For example, if I have to talk of the number of mangoes in a basket, I just need to say the number 20, 25. If I have to talk of the amount of rice in a big bag, I just need to say the kgs, 25 kgs of rice, etc. That's sufficient. Right? The quantity, for example, has been a scalar, the mass, for which I just need to assign a number and that would be sufficient. Or another quantity, temperature. If I have to talk of the temperature in a room, I just need to say the number. The temperature outside is 33 degrees Fahrenheit. That's sufficient. The temperature in the room, if I on an AC, the AC would cool it down and temperature would be 25, 26. That's sufficient. Right? The temperature just needs a number. Let's contrast it with such other quantity with other another quantity. Let's say the wind speed. All right. Have you ever heard of the pilots who are testing? They in their commentary they'll be, I mean, in their while they're relaying the message to the other passengers, they would be saying that actually we are flying at an altitude of 10,000, 31,000 meters above, and the wind is 31 degrees north, going at so and so meter per second, this much wind speed. So they would be also indicating the direction in addition to the speed of the wind, which is the magnitude. Which means whenever I have to talk of the wind, I just don't I just don't end it with the magnitude. I also need to actually tell you the direction in which the wind is moving. So there are certain quantities which require both the magnitude as well as direction. Such quantities are called as vectors. Now, we also know of the, if I have to go in a particular way, the maps, right? You might be seeing the GPS. In GPS, you would note whenever you see the directions, that would show you 100 meters north, 100 meters, 150 meters right of right east, etc. It would show you the direction as well. That means the quantity of the same distance, when it is added with a direction aspect, that becomes a vector. So such quantities we call as vectors, which means it has got both a magnitude and a direction. So why do I have to define our quantity as vector? In what way would it be helpful to me? In what way would it be different? Now, to answer this, let me ask you a question. Suppose I have a tube, and in the tube, I have got, let's say, a ball which is moving at 3 meter per second, right? Now, this is my room, and this is the ball. This is my ball, and that ball is moving at 3 meter per second. Let's say this tube here is at rest. Now, if I ask you, how fast is the ball moving? What would be your answer? Velocity of ball would be equal to 3 meter per second. Now let's say the tube here is also moving backward at a speed of 4 meter per second, right? Now imagine this tube here, this tube as a whole is moving backward at 4 meter per second. Now inside this tube is a small ball which is moving forward or towards the right at 3 meter per second. Now if I ask you what is the net velocity of the ball, right? What is the net VB of the ball? If I ask you this, it won't be 3. Would it be 3? Would it be 7? Would it be anything else? Straight away we know that it won't be 3. Why? Because when this was at rest, this is the velocity of the ball was 3. But now we see that this is also moving backward with a speed of 4 meter per second. So we see here that when I include direction, the quantities, suppose let's talk of a different quantity, right? In contrast to this, in my pocket, I have got $60, and to this, I add another $40 or rupees, anything. Now the net quantity or the net amount would be just 60 plus 40, which would be $100. Now this is what we have been doing so far, right? When we are dealing with scalars, we are just adding them straight away as numbers. 60 plus 40 is 100. Now if I ask you the same question of net velocity, it won't be 3 plus 4 equals to 7, right? This won't be your answer. Although you have two velocities, one as 4, other as 3, the net answer won't be 4 plus 3. Why? We can see it clearly here because this is moving in the tube is moving in the opposite direction, the ball is moving in another direction. The net velocity would be actually minus 4 plus 3, which is minus 1 meter per second, right? So how this is so? It's because of the vector additions. So we need to define quantities as vectors in order to account for such additions where the net additions won't be just the new addition of the numericals or the magnitudes. Okay. Now let me show you a small video here that's going to talk about the same thing.
Physicists, air traffic controllers, and video game creators all have at least one thing in common: vectors. What exactly are they, and why do they matter? To answer, we first need to understand scale. A scalar is a quantity with magnitude. It tells us how much of something there is.
Listen, this is just the magnitude. It's going to tell us how much of this magnitude we have of any quantity.
The distance between you and a bench and the volume and temperature of the beverage in your cup are all described by scalars. Vector quantities also have a magnitude, plus an extra piece of information: direction. To navigate to your bench, you need to know how far away it is and in what direction, not just the distance, but the displacement. What makes vectors special and useful in all sorts of fields is that they don't change based on perspective, but remain invariant to the coordinate system. What does that mean? Let's say you and a friend are moving your tent. You stand on opposite sides, so you're facing in opposite directions.
So as you understand, so far, he has described a property of vectors, which is the direction aspect, right? That's what is required in addition to magnitude, and that's what we need to capture by defining a quantity as vectors. We're going to continue this video once again. We're going to come back to that. There is another, before we go to that, we need to understand certain representations of a vector. So far we know that whenever I talk of a simple quantity such as a scalar, a simple physical quantity like mass, temperature, etc., I just use that algebraic notation. For mass, I have the term m. For temperature, I use T. For volume, I have V. For pressure, I have P. For density, I have rho. For energy, I have E, etc. So all these terms are basically the algebraic symbols which are sufficient to represent my scalars, right? But if I see vectors, vectors need something more. To represent vectors, I need something more. Just algebraic notations are not sufficient. What do I need? I actually need the same algebraic letters with an arrow on top. This indicates that this particular quantity is explaining me that it refers to a vector. Now, it's just simple. I just have an arrow on top of the same algebraic notation, algebraic symbol here. But to understand this, what does this arrow represent? This arrow represents to me that at a particular point, I have got a vector, and this vector is in a direction. For example, if you're talking of the vector direction as distance vector, actually the distance vector becomes displacement to us. And if I got to talk of displacement vector between a point at a point A, if it is pointing in a particular direction, then the tail, this arrow has got a portion called the tail, and this is the head. The tail of it, starting from a given point A, would tell me that this vector is positioned at this point. It's not stretching all around in the space. It's only positioned at this point A, and it is in this particular direction. Now, the magnitude of this vector, or the magnitude of this length of this, is going to tell me the magnitude of this vector A. For example, this is 5 meters, then this length would mean that it is 5 meters. If I am talking of only 1 meter, then proportionate to this vector, I would have to represent it as with a small arrow. Of course, the direction would be different as per the direction of this particular quantity. Now, don't get confused between the vector which is actually spreading all across in the space doesn't mean that it's existing everywhere. It's just present at that point where you have indicated with the tail. That's it. Naturally, whenever we see such representations, we just go off the board, right? We would be thinking, how am I supposed to just make sense of all such directions? And suddenly, why are we talking of arrows with particular directions and all? Why do we need all these things in order to talk of some simple quantity? So to understand this, we're going to look at a very practical example. Suppose you know Google, right? Let's just start with the Google, and I'm talking of the distance between Hyderabad to Chennai. I see here Hyderabad is positioned here, Chennai is here, and is going to show me a particular route in red, which is indicating me that this particular route in blue is going to show me the road distance. Now, there's nothing special about this road distance. It shows me 626 kilometers. I'm going to show you now the flight route. You see this flight route? The flight route is more or less, it's just the straight line path between these 2 points. So it can be called a directional vector, right? And the distance between this Hyderabad and Chennai is more or less, the flight journey is going to be the shortest distance. So such quantities, when I say shortest distance, I'm going to indicate them by a particular vectorial notation. Why? Because you see, it's going to be a straight line, and it has got a starting point, which is Hyderabad, and it has got an end point, which is Chennai. So to represent this, I could say that, this is Hyderabad here, representing by HY, and this is Chennai here, representing by MS. And I have a vector from here to here in this direction, and this length of this vector is going to be the length of the distance between Hyderabad and Chennai, and the direction from Hyderabad to Chennai is going to be the direction of this vector, right? This vector is called my displacement vector from Hyderabad to Chennai. We'll talk about this in future, but just remember it as of now. It's just called a displacement vector represented by S bar. Okay, so how much would this displacement vector be? Now let's go back to Google. We'll just see here. If I right click here at this point, there's an option called measure the distance. And from here, I want to measure till which point. Let's say that is till Chennai, right? So I click it here. And it's going to show me it's about 496.85 kilometers, right? So this displacement vector is about a distance of almost 500 kilometers, let's say, correct? And it has got a direction as well, right? So the displacement vector is going to be unique between 2 points, that it has got a particular magnitude and it has got a direction as well. Now, at the same way, if I talk of the displacement vector from Hyderabad to Vizag, right, that would be something like this. And the proportional, let's say Hyderabad is here and Hyderabad to Vishakhapatnam, correct? So let's change it to Vishakhapatnam. I have the suggestions here. Hyderabad to Vishakhapatnam would be a total of let's measure it once again. That would be a total of 496 once again, 496 kilometers. So it's almost the same distance between Hyderabad and Chennai and Hyderabad and Vishakhapatnam, which means if I talk of the displacement vectors between Hyderabad and Chennai and Hyderabad and Vishakhapatnam, I have to have two vectors which are of the exact same magnitude, which means whatever is the length I use to represent this vector needs to be also represented in the same length. All right. This and this are going to be equal because the two vectors have got same magnitudes. But you see the directions are different. Therefore, I have indicated in another direction. Now, this is what is a vector in short. It just has a magnitude as well as it has got a direction. Clear. Now, let's talk of addition of these vectors. Suppose I go from a point which is here. I go, let's say this is east direction. Suppose I travel a distance of 4 meters east and I travel a distance of 3 meters north, right? The total distance when I move from A to, let's say this is B and this is C here. The total distance between A to C is going to be actually 4, right? If I say net distance is supposed to be the total length of the path. So that would be 4 plus 3, which is going to be 7 meters. But if I have to talk of the value called the net displacement would be actually the summation of this displacement here, which is in this direction, plus this displacement here, which is in this direction, right? So that would be S1 bar plus S2 bar, right? That would be my net displacement. And that won't be equal to 7 here. Why? Because you see this displacement, why? Let's understand why it won't be 7. Simple reason. Although I walked a total distance of 7 kilometers, it's not all in the same direction. It's in different direction. So the total displacement is supposed to be basically the initial and the final point and the direction to that final point. That's it, right? So in the previous case, imagine you were going from Hyderabad to Chennai in bus. The bus distance is not called your displacement vector. Why? Because your bus is going all around from here to here and along this red route. And you see the red route is showing you a distance of total kilometers in the red route is 725. I'm sorry. This distance is total of How much kilometers is it? 621 kilometers, right? This total distance is 621, but we just saw that the displacement was only 496 kilometers between this point and this point. So even though you move all around on this bus track and reach your final destination of Vishakhapatnam, your displacement would just be this straight line path between Hyderabad and Vishakhapatnam. So your displacement would be more or less your aerial distance between the two. More or less, it would be the same 500. So compare the same thing here. You're going from A to B to C, but your total displacement would be just this value here, and that value would be actually 4 plus 3 in vectorial sense, 4 bar plus 3 bar, right? This is just a representation that it is not a just numerical quantity, but instead it's a vectorial quantity. And your answer won't be 4 plus 3, 7. Now your answer should be this value here, right? Because this is east and north, we know this is a right angle triangle. So my total net vector or my total displacement is going to be this value here. And since I know that actually the magnitude of this particular vector is going to be just the length of this part, right? If I represent these two vectors proportionately, I mean this vector and this vector, if I represent them both with the magnitudes 4 and 3 here, the net magnitude is going to be actually the total length of this. And we know by using Pythagoras theorem, that length would be 4 square plus 3 square under root, correct? And that would be 5 meters. So my total displacement is supposed to be just 5 meters. It's not 7 meters, right? This is how we add vector quantities, and that's how vector additions are different. And we need certain quantities as vectors. That's it. So let's just see a few questions here. What wouldn't change a vector? Suppose I have a vector and the vector is not changed if it is rotated through an arbitrary angle, if it is multiplied by an arbitrary scalar, if it is cross multiplied by a unit vector, or if it is split parallel to itself. Let's analyze this with the same example we have taken for a vector, which is the distance between Hyderabad to Vishakhapatnam or Hyderabad to Chennai, right? We call it the displacement vector. Look at the question carefully here. Doing what wouldn't change a vector, right? We have the four options. First, if it is rotated, let's consider the rotation aspect. So if I rotate this vector, let's say this is Hyderabad and this is Vishakhapatnam, and the vector between Hyderabad and Vishakhapatnam was this, right? I'm going to show you here once again. This is Hyderabad and this is Vishakhapatnam, and this was my vector here, right? Now, if I rotate it, see, this is a direction. If I rotate it, it's going to point towards something else. Maybe it's going to go towards Orissa or Bhubaneswar, Kolkata, etc. It's going to be a different vector, right? So rotation would definitely change the vector. Now let's check another option. If it is multiplied by an arbitrary scalar. Now if I multiply it by a scalar, that means let's say I multiply it by 2. That means this vector is no longer going to be pointing from here to here. It would actually be stretched, is it not? This would be pointing to another location somewhere here. So if I look at the case here, Hyderabad to Vishakhapatnam, if this vector is multiplied by twice, so it would be pointing somewhere else, is it not? Because this would be going to somewhere in the sea, right? This was close to 400 kilometers. If I multiply it by 2, it would be a vector pointing till here. That means it's no longer the same displacement vector between Hyderabad and Vishakhapatnam. It's going to be pointing to some other location in the sea, right? So that would also change the vector. If it is cross multiplied by a unit vector, what would happen? Now we haven't seen what is going to happen by cross multiplication. So let's just ignore this option C. Consider it, it's not there. Now look at the third one, fourth one. If it is split parallel to itself, think about it. If I just split the vector, if I just slide the vector in the space with the same direction, this is my direction, Hyderabad to Vishakhapatnam, right? This is my vector. Now if I just slide it parallelly in the space, this vector, if I just keep sliding it, if I slide it, think what will happen. The same vector, I would have the same vector, is it not? the vector would have the same direction between Hyderabad and Visakhapatnam, and it has got the same magnitude. That means it's going to be the same vector. So here comes the condition for equal vectors, or the equal vectors, which means they should have the same magnitude and same direction. Then we say that the magnitudes would, then the vectors would be same. Correct? Same magnitude and same direction. That's what would be unequal vector. Suppose, let's come back to the question I have here. A1 bar plus A2 bar plus A3 bar. If I add all these three, which direction will be my net displacement? So let's understand. Will it be in this direction? Doesn't seem so, because A3 and A1, you see, this and this, resultant of these two is supposed to be somewhat in this direction, because this direction has got a larger quantity. So net displacement of something here and here, it's going to be somewhere in between these two, right? Because I add this and this, imagine vector quantities as forces. Suppose you're pulling something in this direction and you're pulling something in this direction. The ball or the object you're pulling wouldn't be moving in a direction somewhere in between this. That's what we are talking of vector additions. So the net direction won't be either this or this or this, nor this. It would just be somewhat like this. It would be C. Your answer would be C here, right? Think about this one more time, and if you have a question, we can discuss about it once again. Let's show few more things with respect to the same vector quantities. I have a quantity, a vector A bar. Now, if I talk of a stretch vector in the same direction, right? But it's just a multitude of times more than this, or it could be less than this as well. All I have to do is I have to multiply a scalar to this quantity A bar. If I just multiply it with a quantity C, I have a new vector B bar, which is just C times A bar. Now this tells me that the same vector is just stretched, right? So in one sense, multiplying a vector by a scalar is permissible, right? The C here is a scalar, and the new vector would point in the same direction, but then it would have a different magnitude, right? That is called multiplication of a vector by a scalar. This is represented graphically here, if you see, right? The vector is not changing. All that's happening is, imagine the vector being stretched. That's it. Now what happens if I add two vectors in exactly opposite directions? That is, if I add a vector A bar and another vector minus A bar, what would happen? See, imagine this. Suppose you go from Hyderabad to Chennai and then come back from Chennai to Hyderabad. What would be your net displacement? Your net displacement is just supposed to be 0, isn't it? Because you are at the same point from where you started. So your direction, your tail and the head would be at the same point. So your net displacement is 0. That's the same thing being indicated here. You see, A bar is in this direction and minus A bar is just in the opposite direction. So when you add A bar and minus A bar, you see, you're going to come back to the same point. It's a 0 vector, right? Now, suppose I've got a negative direction, I come twice. So I subtract a vector from, I subtract a greater vector, or basically I subtract A bar, 2A bar from A bar. What would happen? It's just a very, integer type of addition. That's it. What happens is just similar. You go this direction till here and then you come back in the opposite direction minus 2A bar. Your net displacement would be this part here, right? It would just be 1 minus 2, which is minus 1 A bar. So you are basically going to be, from your starting point, you're going to be minus A bar in this direction. So multiplication by a negative scalar also doesn't alter anything. All you have is basically a vector which is stretched as well as reversed. That's it. Now, here comes the part where the vectors are not exactly either parallel or anti-parallel. Such vectors, how do we add? So addition of that vectors are going to be, we're going to do that by a method called as the parallelogram law of vectors, which we'll be seeing later. And there's another method called the triangle law of vectors. These two simple laws are going to tell us just figuratively how we can add the vectors, how we can add vectors which are not exactly parallel or anti-parallel, right? So this we'll discuss once again. Let's see another question. So think about it based on the discussion so far. Try to answer this question. Let's revise what we have done. we have discovered a new type of quantities called as vectors, which would need actually magnitude as well as direction, and they are operating by different laws for addition, right? They are represented by a quantity, an algebraic representation. Uh, in addition to that, we would have a short arrow on top of them that would tell us that it's a vector quantity, right? Examples of vector quantities we have seen would be velocities, or we have seen also displacement. Shortly, we would see that acceleration is also another vector quantities. Forces would also be vector quantities. We would see all that once again. And we have seen how, if I multiply it by a scalar, or if I just multiply by a negative scalar, if I add the vector with a negative vector, what would happen, right? So, and we would be seeing the parallelogram law of vectors as well as the triangle law of vectors once again. All right. So I hope this is very simple and easy to understand things. And if you have a doubt, sure, you can get back to me.